Hello, everyone. Welcome to the fourth session of our Cloud Native Launchpad series. Our topic today is Oracle Container Engine for Kubernetes, OKE. In this session, there will be a brief introduction of Kubernetes, followed by details on how OKE is designed to deploy and manage containerized workloads at scale. My name is Renu Bhatt, Program Lead for the Custom Enablement team here at Oracle. And our presenters today are Eli Schilling and Chip Huang. With that, please enjoy the session. Eli, please take it forward.
Awesome. Thanks, Renu. And welcome, everyone. This is our Kubernetes Management Made Easy with the Oracle Container Engine for Kubernetes session. Looking forward to diving in and having some discussions with folks today. My name is Eli Schilling. I'm a developer advocate here at Oracle, focused on cloud native and DevOps. And I'm joined by my colleague, Chip. Chip, how about a quick intro from you, sir?
Oh yeah, hi. My name is Chip Wong. I'm with the partner marketing team. Glad to meet all of you.
All right. So remember, we're continuing our cloud native journey here. We did the managing code previously, which was recorded and posted. Today, we're going to talk about Kubernetes management made easy with OKE. Next session will be on serverless apps with OCI functions, and we will wrap up the series with an OCI DevOps overview. So please come back and join us for those. Objectives for today, we're going to talk about the key concepts and use cases for Kubernetes. We'll take a look at the managed service that Oracle offers for simplifying provisioning and management of your Kubernetes workloads. We'll talk about some of the network design considerations and implementation techniques. We'll do a demo of provisioning a Kubernetes cluster and talk about some of the service capabilities. And then we'll wrap up with an overview of some different deployment options and tools. So with that, we're going to launch a quick poll here, and then we're going to jump in. If you get a minute, please respond to the. And while we're doing that, let's just have a quick summary of Kubernetes. So this Kubernetes, maybe you've heard about containerization, containerized workloads. Really, it's about scaling your application components down to the smallest executable size in the form of a container. But one of the challenges with that was being able to schedule and orchestrate containerized applications at a large scale. So Kubernetes was an open source system that was developed to solve that challenge. It's become pretty much synonymous with cloud native over the past 5, 6, maybe 7 years. And this is an open source project that's maintained by folks within the Cloud Native Compute Foundation. And it's pretty much become mainstream in terms of container orchestration. So beyond kind of the cloud native application space, there's a lot of other useful functions or workloads that could be considered, from things like batch processing, security operations, consuming large-scale compute clusters, like for high-performance compute clusters, for GPU-based workloads, and even managing and maintaining things like databases within your application ecosystem. Kubernetes has been around for quite some time. As of this year, we're expecting about 75% of enterprises will be using some sort of containerized workload. And within the next couple of years, most organizations will likely have some sort of containerized workload in their environment. Now, when we think about adopting Kubernetes and microservices applications, you could certainly deploy an application on Kubernetes as is, but it's really not. That's not really the intent for taking advantage of the capabilities of a containerized orchestration system like Kubernetes. So we really want to think about, how do we start to deconstruct our applications into more manageable components? Think about managing by state, by dependencies, by resource requirements. We're going to start to plan what that allocation, what that distribution looks like. What are we going to connect to? How are we going to interface with the rest of our application ecosystem? Maybe we want to think about automating with infrastructure as code, which we talked about 2 sessions ago. Always want to start with a pilot. So we're just going to experiment, deploy a small scale workload, see how it runs inside of the Kubernetes ecosystem, become familiar with the operations requirements, the operational tasks, begin to develop runbooks, troubleshooting tasks, and standard operating procedures. and then we can begin to sort of formalize and iterate through as we scale into a wider workload adoption. Now, when we think about what the thing looks like under the covers, when we deploy a Kubernetes cluster, what are the things that are present in that ecosystem? So we're going to have a control plane, which consists of our API server, our cloud controllers, a scheduler, and other underlying resources. And then we're going to provision a collection of worker nodes. These are typically compute instances, virtual machines in our cloud environment. That is going to contain a kubelet, which is used for interacting with the API server in the control plane, and then the container runtime itself, which is actually going to be supporting and running the pods that we schedule inside of our system here. Now there's a CLI, a command line tool called kubectl that we generally use for interacting with the API server. So that allows us to view the resources, provision or deploy new services, new applications, and control the resources inside of our Kubernetes cluster. If you're working in a cloud environment, which we are in this case, OCI specifically, there are generally integrations with the rest of the ecosystem to take advantage of services like file storage service, block storage, the OCI load balancer, and other resources to make it easier to extend your application into the cloud environment and take advantage of all of the capabilities and benefits that are available therein. So just a couple things. Pods, these are essentially the smallest unit of resource that we schedule, that we deploy onto a Kubernetes cluster. And this is generally a collection of one or more containers that support and manage our application. Containers in the same pod will share the namespace and underlying storage if we attach storage to it. And this is generally how we would isolate each component in our application workload. Now, a pod is generally it's a scalable resource. So if I need, an increase in amount of capacity for a period of time, we would allow or tell our Kubernetes cluster to simply scale the number of pods, and we would add enough pods to handle the required capacity. So it allows us to easily and quickly scale out and scale back in when the resource requirement is not there. We'll talk about networking in a little bit more detail later, but essentially each pod is going to be assigned a unique IP address based on our CNI, our network interface for our cluster. And that allows us to define how the pods are going to communicate with each other and potentially other resources inside of our environment. If we take a look at containers versus pods just really quick, because if you're working, with something like Docker or Podman on a local system, you're generally just running a single container at a time. And each of those containers running inside the container runtime operate individually and would need to communicate over whatever network interface is defined for those pods, or for those containers, I'm sorry. When we think about the pod model, this is, each pod itself is allocated a unique network endpoint or network IP address, but we can have multiple containers inside a single pod that communicate automatically with each other. So we might have a certain situation where there's a sidecar running, and that's basically an application that's going to be supporting the primary application function. So as a user request or as a command comes into the pod, the primary interface could receive that request, offload to the sidecar container in the same pod, and then continue processing additional requests. Now, one of the challenges with Kubernetes is, deploying, managing, and operating at scale. If you decide to install Kubernetes yourself, it's absolutely feasible. You would deploy on a compute resource, you would provision additional compute instances for the worker nodes, and you control and take care of all of the underlying configuration, performance, patching, scalability. The list kind of goes on. So we implemented the container engine for Kubernetes to simplify and offload a lot of those administrative tasks, make it easier and more cost-effective in many cases to run Kubernetes in the cloud. So with that, we're going to take a quick look at OKE itself, and I think we have one more poll question due up. Thank you. So while folks are thinking about that poll question, a quick reminder, 48 regions currently, more on the way, and 12 regions with the Azure Interconnect, again, giving you the flexibility and the freedom to run this pretty much anywhere in the world, wherever it suits your needs. So OKE, again, this is meant to simplify Kubernetes at scale. We've basically taken the open source Kubernetes software and built a management and control plane around that. That gives us the ability, to institute built-in management, scalability and reliability, and advanced security, taking advantage of a number of the cloud resources that are available within this ecosystem. Now, inside of OKE, we have, as I mentioned, we provision our nodes that are going to run the pods that we schedule. And we have the option of either managed nodes, which are going to be virtual machines or compute instances that you would provision as part of the cluster. And this is going to give you a little bit more control, but also a little bit more administrative overhead. So you have to define how those resources are going to scale. You would be responsible for the underlying security and management of those worker nodes. There's also the option to implement virtual nodes. And that is, you can see here, Oracle then takes on managing the underlying compute resources, patching, scaling, monitoring. We maintain the data plane. So in terms of coordinating and draining pods when there's an upgrade or a resource failure or a migration, that's all done automatically with the virtual nodes. And really all you have to worry about is your access control, your storage volumes, and scheduling your pods. So it does help to simplify further simplify the administrative requirements while also implementing seamless scalability. And if we just dig a little bit deeper here, you can kind of think about virtual nodes as a serverless experience. So when you provision a virtual node, you'll specify a shape and some scalability parameters, and then we will automatically manage and maintain that resource and scale accordingly based on the pods and the Kubernetes resources that you're scheduling onto that underlying virtual node. Another feature that also helps implement a better layer of security while also helping to streamline some of your access control is the notion of a workload identity. So in the cloud, you can assign resource principals to things like compute resources that allow those compute resources to essentially authenticate and authorize against the OCI APIs to interact with other services in the cloud. With Kubernetes, we want to be a little bit we want more fine-grained control. We only want a specific pod to be able to interact with OCI services based on our application design. So we can provision a workload identity, which essentially authorizes specific pods in our cluster with fine-grained access control to access the resources that they might need to interact with in the cloud. That could be an object storage bucket. That could be something like the OCI streaming services for message production and consumption, or other application components that are outside of Kubernetes, but in scope for your particular application. The nice thing about this is it is another resource principal in a sense. And so any API call that's made from your application on that Kubernetes pod is actually going to be tracked by our OCI audit log service. So you can always see what's happening at the API level from your application running on the Kubernetes pod. Now, there might also be situations where you need a custom configuration for your compute or your network resources. This is why we provide the ability to bring self-managed nodes. You can also think about this as kind of a BYON, or bring your own node. It allows you to create the compute resources, configure them the way that you need. That might include an RDMA cluster network, for example. If you're running some high-performance compute workloads or some GPU-intensive workloads, you can provision the cluster network and the compute instances ahead of time and simply bring them into your cluster and register them, at which point you can begin to schedule pods and schedule workloads on those nodes. Now, if we dig a little bit deeper into the integration with OCI, you'll see here the cluster itself, the control plane is fully managed by OCI. The data plane is again, the nodes, whether they're self-managed or managed nodes or the virtual nodes. And then we have integration with things like identity and access management, the OCI DevOps service, encryption if you're using something like the OCI Key Vault. You can also use the secrets manager for essentially registering a Kubernetes secret that's stored in a secure location. And we'll take a look at the load balancer service as well. So when you want to expose your applications out to either other services or out to the public internet, you can simply tell Kubernetes to use the service type of load balancer, and it will actually go out and create the OCI load balancer for you automatically and integrate with the service. All right, I just need to draw this out really quick to show, again, from a developer perspective, the ecosystem within OCI is really all about open source, open choice. So bring the language of your choice, any open source tools that you might be using today, you can bring those along and use them within our cloud ecosystem. And we provide a variety of services and features to help augment and enhance your application ecosystem to help simplify your deployment, management, and operation activities. Now, I'm going to take a quick pause just because I want to do a demo. Let's jump over to our OCI cloud here. And you can see I have simply previously navigated into the, this is under developer services, under containers and artifacts. And this will bring me to my OKE console. I have a couple clusters running already, but we'll come back to those. I just want to show the process of creating a new cluster. We have a quick create option, which automatically generates all of the networking resources, provisions your cluster and your first node pool. If you already have your underlying network infrastructure set up, this could include private connectivity back to on-premises over a VPN or a fast connect circuit, or it might include a cloud-to-cloud connection between something like OCI and Azure. You could use the custom create, which is then going to prompt you to select which networking resources you'd like to use to provision your cluster. So for this, we'll just do the quick create. I'll hit submit. It's going to ask me a few questions. Oop, there we go. So give it a name. We want to define whether the Kubernetes API is public or private. So if we have regulated workloads and we don't want to expose this API to the public internet, we could put this into a private subnet and then access it from the OCI Cloud Shell, access it from on-premises, or maybe a Bastion server that we've provisioned into our VCN. For this, we'll just use public, and then we're going to use the managed nodes. Most often, we'd like to keep our worker nodes in a private subnet. We want to expose those to the internet through a load balancer, or maybe even not at all. So for security reasons, I typically always provision into a private subnet. We'll pick the shape for our worker nodes here. My preference is always the flex shapes because that allows me to simply specify exactly how much compute and memory I'd like to use. In this case, we want plenty of compute, but we don't need a whole lot of memory. So we'll keep that to a minimum. Oh, there we go. Node count, we'll just start with 2 for this one. And there we go. We get a summary of all the resources. We're going to create a separate subnet, one for the worker nodes, a separate subnet for the load balancer services, and then a separate subnet for the Kubernetes API endpoints. With that, we'll just hit create. And it'll take a couple of minutes here. Initiate the process. We can close the window and you'll see my cluster is currently creating. This will take a few minutes, so we're going to jump back over and I am going to pass it off to my colleague Chip to take us through the networking topic here. Chip?
Awesome. Thank you, Eli. So when it comes to networking for OCI, at the core of it is what is the Virtual Cloud Network, or VCN. So the VCN is a private network that you deploy in compartment, and it serves as the basis of hosting all your resources that you're deploying OCI. Now, when you start to create the VCN, the first thing you have to look at is what is the IP address block I want to assign to it. And when you do that, there's several considerations that you have to look into. Well, first of all, with the VCN for the subnet, you can either select a /16 up down to as little as a /30 network for IP addressing. And some of the things you have to think about is like how many devices am I hosting on the VCN? And the reason for this is like every component you deploy with your VCN, all the way from the pods to the load balancers to the worker nodes, they all need an IP address. So you do need an IP address block big enough to be able to support all of these components. Now, another thing to consider when you create a VCN or for the IP addressing range is also, are you going to be connecting to other networks? Are you going to be connecting to other VCNs? Are you going to be connecting to some data centers? And the reason for this, if you need to connect your VCN to other networks, you need to make sure there's nothing overlapping. They cannot use the same IP address range. Now, after selecting your IP address block, the next thing is really start creating subnets. And a subnet is a logical subdivision of the IP block that you just allocated. And typically the reason you want to create subnet is because you want to group like devices together. So for example, for all your worker nodes, you may want to have one subnet there. For your database, you may have another subnet. And for your Kubernetes API endpoint, there's another subnet. And the reason for this is traditionally, when it comes to security, you create your boundaries around your subnets itself. So that's the reason why you want to have this particular grouping. Now, depending on how your application is deployed, whether it needs to be accessible by the outside world, by the internet, or need to access other services within OCI, there's also other components you need to deploy. For example, things are load balancers and service gateway that we'll talk about a little bit more in subsequent slides. And also another thing to consider is which region you're deploying your OKE cluster to. Because depending on the region, you may have different different numbers of availability zones. So think of availability zone as a set of data centers that spread out geographically. And what this allows you to do is allow you to create your VCN across multiple available domains so you can provide redundancy to your application. In case a particular data center fail, there's other data centers to pick up that slack. Next slide, please. Now, let's take a deeper look in what it looks like when you deploy an OKE cluster across multiple availability zones. One of the first things you'll notice that a particular subnet can either span a single availability zone or span multiple availability zones. And this is actually a good, this is actually having the ability to be able to spread your subnet across multiple availability zones actually can simplify deployment. Because now you can group like devices together across multiple availability zones with fewer subnets, simplifying your deployment. Now, as I mentioned previously, when it comes to subnet, it's really it's the reason you're building them is really for security boundaries. And from an OCI perspective, you can create boundaries around subnets using what's called security lists. So security lists are policies that you assign for each subnet that tells what network traffic come in and what network traffic come out. Now, an example for this, like if you have your Kubernetes nodes in one subnet, you have a database subnet, and you also have a load balance subnet. In this case, because the only interaction that you will have for a database is direct from clusters and not from your load balancers, so you want to make sure you have security lists in place that only allows traffic to the database subnet through the OKE worker node subnet. Now, if security list is not granular enough for you, we also have something what's called security groups. And security groups allow you to define policies for network traffic rather than around the subnet, but directly on VNets themselves. And since VNets are assigned directly to hosts, in that sense, you're able to apply policy for network traffic directly to hosts themselves. This is a more granular approach, but because of the more granular approach, there's also more to manage as well. So these are the two things you need to think about when you're creating these security boundaries. But because we do have security lists as well as security groups, you do have the flexibility to customize it to the exact needs for your particular environment. Next slide, please. So we previously mentioned that in addition to the VCN subnet, there may be additional components you may need to use. And this really depends on how your application deploys within your OKE cluster. Now, for example, let's take a step back. So up till now, when we talk about IP addressing, it's really about private addressing. And private addressing is really known within your VCN. So if you need devices to be able to access your application to a private network, you need to assign what's called a public IP address. The public IP address is something known to the worldwide internet, and it's something that you can reserve from OCI. And this is, of course, additional cost to it. Now, typically, if you want your application to be accessed from the external world, you need to what's called a load balancer. A load balancer essentially is your entry point for the World Wide Web to be able to access your application. And because of this, it does require the public IP address. Now, because your VCN is interacting with the World Wide Web, you also need a device to facilitate that particular interaction. And this has come to our first gateway, which is called the Internet Gateway. The Internet Gateway is essentially a router that allows your VCN to talk with the public internet. Now, when we talk about public IP address, they're assigned to devices that need to be directly accessible on the internet. So in this case, it would be the load balancer. But there are instances in which your worker nodes or your pods need to access the internet. In this case, they do not need to be accessed directly internet, but they need to reach out to the internet. Now, for this, we need another device, and that's called a NAT gateway. What a NAT gateway does, essentially, it takes the traffic in terms of VCN that needs to access the internet. It actually transfers a public IP address and interacts with an internet gateway to reach out to the outside world. So if you have your VPN to access outside world, you do need a device called a NAT gateway. And finally, this takes us to what is called a service gateway. Now, if your OKE cluster or your application need to interact with other services within OCI. So for example, if you need to access a storage bucket, typically you would actually go through the internet to be able to access the bucket. But what the service gateway allows you to do is rather than going to the internet gateway to access other OCI resources, essentially provides you a private way to go through the internal OCI network to access these services. So what the service gateway is provides you is, first of all, more security, and secondly, faster access for your VCN to access other OCI resources. Next slide, please. So as Eli mentioned earlier, within Kubernetes there are things known as pods, and every time you spin up a pod, they do require an IP address. And these IP addresses are used for pods to, first of all, be able to communicate with one another, like a pod to connect to other pod, or be able to connect to other services, or even the worker nodes themselves. Now, the addressing for these pods will vary depending on the CNI used, what are known as container network interfaces. So think of a CNI as a network driver for your Kubernetes environment. Now, the addressing itself will really depending on the CNI used. And with OCI, we do give you the choice of two CNIs that you can select at the beginning when you create your OKE cluster. Next slide, please. So this first CNI we provide you is what's called pod networking. And with pod networking, essentially every pod is provided with an IP address as part of your VCN. Now, the advantage of using the pod networking is that when a pod needs to access other services or other components of VCN, it has direct access to it because of using the IP address directly from the VCN. You can also use other services to interact with the IP address. So for example, you can use like the flow logs to look like communication between the pods and other services within OCI. You can also use security groups and access lists to control access between pods to other services as well. The drawback in this case is that because it does require an IP address within the VCN, if your subnet is not sized large enough, it could run out IP addresses. And essentially when the IP address is run a subnet, well, it will keep you from it'll keep you from allocating more pods. So this is one drawback when you're using the pod networking OCI native CNI. Next slide, please. So the other option we offer within OKE is what's called Flannel. So Flannel works a little differently than the native pod networking. And what it does is it actually create an overlay network specifically for the pods. So internally, if a pod needs to connect to another pod within the same cluster, it basically used to have a direct connection. But if it needs to flow and talk to another pod within another node, there needs to be some sort of tunneling as well as network translation. And because of that, there is some latency that's involved when using Flannel. And on top of that, because the IP addressing range you use is not aware by the VCN, essentially you cannot use other VCN services such as security group access list to be able to secure the connectivity between them. But the great thing about the Flannel is that you don't have to worry about pods taking up additional IP addresses within the VCN. So in case that you may have a really large deployment that have a lot of pods, you may want to consider using Flannel so you don't run into IP exhaustion for when you're deploying pods. And within OKE, there's also a third option here. Let's say you don't want to use Flannel, you don't want to use the native pod networking, you can disable the CNI that's within OKE and bring your own CNI. So for example, you can actually bring something like Calico, or Cilium in this case, if you're looking for specific capabilities from those particular CNIs. Like for example, with both Cilium and Calico, there's built-in capabilities to run network policies that we'll talk a little bit later. Next slide, please. So we talked about the load balancer. And as I mentioned previously, load balancer is really a way for the outside world to be able to access the application. And within OCI, there's actually different flavors of load balancers. You can either have a load balancer that functions on layer 3 or function on layer 4. And it really depends on your need application. Typically, with things like HTTP access, you do want to have something at the layer 4. And the reason is because you want to preserve that session information as it's transferred between pods. So for those particular cases, you would want to use something around layer 4. You also have the option using just layer 3 load balancers. And these for applications such as the UDP or maybe just IP applications not require the layer 4 session connectivity. Now, layer 3 has its benefits in terms of it is faster, but layer 4 does provide you with that session connectivity that's required for most applications. Next slide, please. And finally, let's talk about Ingress security. Now, within any Kubernetes cluster, whether it's OKE or anything else, you do have a device what's called an Ingress controller. Now, the purpose of Ingress controller is really to act like the application router. As traffic, so let's say, for example, within your OKE cluster, you have multiple applications there. The Ingress controller acts as your entry points and essentially will forward the traffic to the right application. Now, typically, an Ingress controller is tied directly to the load balancer. And the reason for this is with a public IP address with associated load balancers, there's usually a cost associated with it. There may also be limitability. So if you have multiple applications within your OKE clusters, you do not want to have a separate load balance for each. You do not want a separate public IP address for each because that will incur additional costs and there'll be a lot more to manage. So having Ingress controller essentially allows you to consolidate all the entry point for all your application into a single public IP address. And on top of that, with Ingress controller, it can't work with other components. So for example, it can integrate with a firewall, so it can act as like a firewall for your application as well. If you happen to use TLS or SSL, it can also process your TLS and SSL termination rather than putting that functionality into your application. So a centralized way to be able to do TLS and SSL. And with most Ingress controller, you can also integrate directly with a certificate manager to rotate certificates. Now, with OKE, it pretty much works with any well-known Ingress controller out there, things like Nginx, the Trafic. So you essentially can bring your own Ingress controller to your OKE cluster. Next slide, please. So with OKE, you still also have the option of what's called a native Ingress controller. And this is an Ingress controller we built specifically OKE that had better integration with other services. So our native Ingress controller integrates with our certificate manager, integrates with a particular firewall. It also provides additional benefit as well. So one thing about native controller, it is aware of the IP addressing of our pods. So typically with the bringing on, when the load balancer forwards traffic to it, it needs to first look at the traffic and then decide which pod to send to. It does create additional latency in there. With our Ingress controller, it knows exactly which node which pod to send to, and essentially it can save that additional layer of latency. Next slide, please. So this is a feature that we recently just launched not too long ago. And what OKE network path analysis allows you to do is really test the network connectivity between different IP addresses to your application. So if you happen to have, let's say, a misconfigured security group or misconfigured security list, network path analyzer can tell you where that particular connecting is broken. So much easier in terms of troubleshooting. Next slide, please. So we mentioned earlier about security lists and security groups. These are primarily used to control traffic between OCI resources or resources outside of OCI to talk to your worker nodes or specifically OCI resources. But in order to control traffic within your OKE cluster themselves, for example, if you want to have only traffic from certain namespaces people talk to each other, you would use what's called a network policies. A network policy would define access within your pod based on different things. For example, IP addresses, namespaces, or any other OCI resources. Now, deploying for network policy within OKE, you do need to install a plugin. For example, you can deploy a Calico plugin in this case, but it's a very straightforward approach. Essentially, you can download the Helm chart, you can run the Helm chart, and essentially that will deploy that capability in your cluster. And from there, network policy are defined as a Kubernetes resource. Next slide, please. And finally, we're just kind of coming back to security groups. So security groups is a way for you to be able to control access on the VNet level. And with that, you can control access for things like API endpoints, worker nodes, load balancers. And if your pod happen to use native networking and have the IP to the VCN, you can also use security groups to control access for that as well.
Let's just jump back over to the conference has been successfully provisioned. Take a look at the node pool. This should be just about, if not done. We've got two of our nodes here. So let's just take a quick look at the contents here. And if I want to access this cluster, we make it very simple. I just open up the dialog box here, and we have an OCI CLI command that's going to retrieve the cluster configuration and write it to our kubeconfig file. We'll just copy that and run it. And it's probably going to tell us we already have a kubeconfig file. We just merge the changes into it. I do have a handful of clusters running. So if I'm working with multiple clusters, this is all, at this point, Kubernetes functionality. So I'll do a kubectl config get contexts. And you can see here that I have a handful of different clusters in my kubeconfig. And this just makes it easy for me to define the context and be able to move between and manage different clusters. So this context here is the one we just created. You can see the little asterisk on the side indicating that that is the current context in use. So we'll do a kubeconfig, let's see, rename context. Oops, let's give it the context, cloud coaching 002. It helps if I type it properly. All right. Now, we all see what happens if I mistype something. There's a lot of text going into this. I actually like to create aliases. So rather than something like kubectl get pods, well, in this case, config use context. Let's switch back to my other cluster where I know I have some pods running. Here I could do an alias. This is just a shell alias. Kubectl get pods equals done. Now, if I just run kgp, voila, much less typing required. These are just part of the bash profile. So if you do exit the Cloud Shell and re-enter, you do have to type those again, or you can put them in your bash RC file so that they're automatically loaded. But that's just a kind of an admin tip so that folks who are interacting with Kubernetes a lot, it makes life a little bit easier. Let's jump back over to the other context though, because we want to deploy some stuff on this cluster. And we're going to start with an Ingress controller that Chip told us about here. So just grab my command. In this case, we're just going to use the Nginx Ingress controller. It's stored and maintained on GitHub, so it's easy enough just to perform a kubectl apply and then reference the URL of that YAML file. And it's going to go grab the details and create a whole bunch of resources. So you'll see here, creates a cluster role. It binds that role to the Nginx Ingress admission controller. And now if we actually run git pods, oops. We'll see here that I have a new namespace called Ingress Nginx, and then I have a handful of pods here that are going to be our Ingress controller. So as Chip mentioned, with the open source or third-party Ingress controllers, they do run as pods on your cluster. So they're exposed via the OCI load balancer, and the incoming traffic is going to be routed by the load balancer to the pod, the Ingress controller. And then the pod, based on the rules you specify, will route that request to the appropriate service or application pod, depending upon how you have it configured. If you do use the OCI native Ingress controller, there's no additional resources running on your cluster. So all of that, all the configuration and all of the Ingress routing decision-making happens outside your cluster. So it does reduce the latency a little bit there. Now that I have my Ingress controller running, if we wanted to deploy an application, actually, let's take a quick look at the Ingress service. So you can see here, if we wanted to get some details about that. There we go. So you can see that the details of my Ingress controller. Actually, what I want to show you is not there. Let's just get the service. All right, so we're going to get the service details. You'll see here it gives me a public IP address, and that's going to be the OCI load balancer that was created automatically when we provisioned the Ingress, the Nginx controller to our cluster. If we deploy an application now, let me just, I have a Helm chart here. So Helm is another service, another tool that allows us to define what our application components will be, and we can pass a values file into that so that we can alter or implement specific parameter values when we actually deploy this. So it makes it easy to have a single application definition and then use different values, YAML files, to deploy test environments, production environments. So you can change the size and the shape and the configuration of your application simply by altering or passing a specific set of values when you deploy the Helm chart. So this is going to be a simple little web app that basically takes. Let's get the pods, and you'll see here I have MooShop. There's an API, some assets, Edge, and storefront. So now if I take the public IP address of that load balancer, open a new browser tab, voila, here is my application, my MooShop application, running on my OKE cluster. And all the traffic is flowing through that Ingress controller, and it is controlling, you can see here in the little graphic, which backend resource is being accessed depending upon how I'm navigating this simple e-commerce site, this example. So pretty slick. That, of course, is all just Kubernetes functionality, but because we're running this inside of a managed service, I don't have to really deal with any of the other, deploying and controlling and managing the underlying infrastructure itself. One of the other benefits I just wanted to show quickly was the notion of cluster add-ons. So this is another feature that OCI has implemented to make it easier to essentially implement additional third-party tools on the cluster. And these add-ons are all available where Oracle will maintain the version control, the implementation, and all the access control to these resources. All I have to do is pick which add-on I want. Let's do the autoscaler, and hit enable. I can either pick my own version where we can bind this to a particular version, or I can let Oracle just take care of that for me. If updates are available, those will be applied without any interruption to my cluster, my service here. I do need one parameter really quick. So I'm going to allow my node pool here to automatically scale. The cluster autoscaler is going to provide functionality to add or remove compute resources based on on pod scheduling. So I don't want to have to add more compute resources myself or set up some, complicated solution. I can simply activate cluster autoscaling, define a few parameters, and let the plugin take care of all that for me. So I do need my node pool ID. This is going to tell the cluster autoscaler the scope of what I'm allowed to scale up and scale down. So I'll go back to my add-ons. We're going to activate the cluster autoscaler. So you can see the instructions here. Once I enable it, it does say I want to specify the minimum number of nodes, followed by the maximum number of nodes, followed by the OCID of my node pool. And if I have multiple node pools that I'm wanting to use with the autoscaler, I can simply put a comma and repeat that same pattern. So we'll start with 2, we'll scale to 10, specify the node pool OCID, and we'll save that. And if I go back and look at my pods, let's see, get pods, and we'll look at the cube system namespace. You'll see that we're implementing a cluster autoscaler pod that's going to be handling all that for us. So this does take a minute to create. While that's creating, I do just want to show there's a couple of policies required. So this is basically where we're going to allocate a resource principal to our cluster. And this can be done either with a more traditional dynamic group, which is assigning a resource principal at the underlying compute instance, which is what I've done for this example. Or you can use the workload identity feature that I talked about to allow you to assign the resource principal to the cluster autoscaler pod specifically. That way, no other application component on your cluster can accidentally perform tasks that would affect your compute resources. So the dynamic group is essentially going to include a matching rule that will match all compute instances in my OKE cluster. And then the permissions I'm assigning essentially allow it to manage the node pool, manage compute resources, and use the subnets in my compute or my VCN to place new compute resources. That should be running now. All right. And if we wanted to make this scale, let's go to our node pool really quick. And we have 2 total worker nodes. So I just want to scale one of my deployments here. All right. So I'm going to scale the MooShop Edge pods. Right now I just have the 1. But if I say, give me 50 of those, the resource specifications in my deployment are going to be such that I don't have enough compute capacity. So if I get the pods, you'll see we're creating a whole bunch of edge pods here. Some of them are creating, some of them are running, and quite a few of them are still pending, simply because we don't have compute capacity to run all of those pods at present. So you can see here within a matter of seconds, the node pool is going to be updating, and it's actually provisioning another compute resource. So this is what the cluster autoscaler is going to do for us when I specify, when I try to provision or schedule more pods than my infrastructure can handle. The cluster autoscaler adds more compute capacity in order to schedule those pods. And these will sit here in pending status until my new compute resource is available, at which time Kubernetes will check back, schedule the remaining pods, and we'll be up and running. Now, if I were to scale my application back in down to 1 or 2 pods, and I no longer need the compute resources, after a period of time, the cluster autoscaler would identify that we have additional unnecessary compute resources, and it would scale back in and remove that capacity. All right, I know we're getting close to time here, so I do want to show just a couple more things. Deployment methods. kubectl, if you're just experimenting, you can create deployments, you can deploy pods. The CLI is a really great tool for just kind of poking around and familiarizing yourself with your cluster. Once you start to define common application patterns or reusable application deployments, you would generate YAML files that basically specify what kind of deployment you're going to be doing, how many replicas, if there's a node selector that you're going to pick from, your container image, your application resources, and so on. So you would write those files and simply say kubectl apply, and then specify the file name. We looked at Helm as well. This is just an example of the deployment looks like. So instead of specifying a hard-coded value, I would put a placeholder there, and then my values YAML rate the key value that I want to apply when initiating that deployment. More fun stuff. If you're using Terraform or infrastructure as code, as we talked about in a previous session, there is a Terraform provider for Kubernetes and a Terraform provider for Helm. So this again, I could have my application, I could have my infrastructure as code, not only provision my Kubernetes cluster, but also apply my Kubernetes config or my Helm charts to deploy my application once the cluster is up and running. So all of that, especially for non-production environments where I want to stand up a test environment or a dev environment, all of that's configured as infrastructure as code. I run one command, and all my infrastructure is there. My application is deployed, and I can begin my testing pretty quick. So that does bring us to the end of the show for today. We'll hang on for a few minutes if there's any more questions, but I hope everyone now is familiar with some of the key concepts of Kubernetes. You understand a little more about the OKE service that we offer, that you're more familiar or hopefully comfortable with some of the network design considerations that Chip shared. And we hope you enjoyed the demo of provisioning a cluster, deploying some applications. And again, I highly recommend making use of those aliases, because you'll find when you're using kubectl for long periods of time, it's a lot of typing. So anything to make your life easier, give it a shot, go check it out. So with that, I will throw a few more slides here. We do have a public Slack channel if you want to come chat with us, ask us questions. A bunch of cool resources at developer.oracle.com, and definitely, more resources, free tier accounts. Please be sure to check that out and get to know OCI a little bit better. Chip, any parting thoughts from you, sir?
Oh, no, I think you covered it really well.
Excellent. Thanks for your help today. Renu, I pass it back to you.
Thank you, Eli and Chip, for explaining everything in such a simple manner. Really appreciate that. I hope everyone enjoyed this session and learned something new today. Our next webinar will be on Monday, April 1st, where you'll learn about building and deploying serverless apps with OCI functions. So if you're interested, please do not forget to register for that session. I recommend that you bookmark the Day One and Beyond page and check frequently for new sessions on trending topics. Great. Thank you, everyone, for joining us one more time. Hopefully, we'll see you for our next webinar. See you all next time. Have a great day, everyone.